Hello students, most welcome to Dr. Acharya Academy. Today I am going to discuss the hybridization of atomic orbitals. Today's class number is 082. In order to explain the characteristics, geometrical shapes of polyatomic molecules like methane, ammonia, and water, Pauling introduced the concept of hybridization. So, what is hybridization? Hybridization means a set of atomic orbitals will form a new set of equivalent orbital, which is known as hybrid orbitals. Unlike pure orbitals, these hybrid orbitals are used in bond formation, and this phenomenon is known as hybridization. It means whatever the atomic orbitals are there, a number of atomic orbitals will form same number of equivalent orbitals by hybridization. So, hybridization can be defined as the process of intermixing of the orbitals of slightly different energies. You have to remember this. The atomic orbitals which will be intermixed to form hybrid orbitals, those atomic orbitals should have slightly different energies so as to redistribute their energies and resulting in the formation of this new set of orbitals of equivalent energies and shape. So hybrid orbitals always have equivalent energies and similar in shape. Example, very common example, when 1 2s orbitals and 3 numbers of p orbitals of carbon hybridized, there is the formation of 4 numbers of new Sp3 hybrid orbitals. Here we need to remember that what is the total number of atomic orbitals participate in this hybridization. That total number will be equal to the number of the new hybrid orbitals. Here 1 2s orbitals and 3 2p orbitals, that is total number of atomic orbitals participate in this hybridization is 4. So new Sp3 hybrid orbitals is total number also 4. There is some features of hybridization. Number 1, the number of hybrid orbitals is equal to the number of the atomic orbitals that get hybridized. I already explained it. Point number 2, the hybridized orbitals are always equivalent in energy and shape. Third point, the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. Number 4, these hybrid orbitals are directed in space. That means in spatial in nature, in some preferred direction to have minimum repulsion between electron pairs and thus a stable arrangement. Therefore, the type of hybridization indicates the geometry of the molecules. Most important condition for hybridization. Number 1, the orbitals present in the valence shell of the atom are hybridized. Number 2 condition, second condition, the orbitals undergoing hybridization should have almost equal energy. Third condition, promotion of electron is not essential condition prior to hybridization. And last condition number 4, it is not necessary that only half-filled orbitals participate in hybridization. In some case, even filled orbitals valence shell, that means sometimes the lone pair, this also takes part in hybridization. Now we'll discuss about the type of hybridization. Hybridization involved with sp d orbitals. When s and p orbitals participate, especially for the representative elements, in this case 3 types of hybridization happen: sp hybridization, Sp2 hybridization, and Sp3 hybridization. And right side, you can see when with sp orbitals, d orbitals also participate, then this type of hybridization also can happen. And this I'll discuss in the next class. Today I'll discuss only these 3 types of hybridization where only s and p orbitals participate to form hybridized orbitals. First number, sp hybridization. This type of hybridization involves the mixing of one s and one p orbital, resulting in the formation of 2 equivalent sp hybrid orbitals. The suitable orbitals for sp hybridization are s and pz if the hybrid orbitals are to lie along the z axis. This is the z axis. So pz orbitals will direct participate to form the sp hybrid orbitals. This is the example of the beryllium. So sp hybrid orbitals, it has 50% s character and 50% p character. This character, s character, in this hybridized orbitals is 50%, and this p characters also in hybridized orbitals it also 50%. That means 50-50. Such a molecule in which the central atom is sp hybridized and linked directly to 2 other central atoms possess linear geometry. So this is the linear geometry. And this type of hybridization is also known as diagonal hybridization. And the 2 sp hybrids points in the opposite direction. You can see this direction is this side, and for p orbitals this is this side, and ultimately whatever the resultant is there, these 2 sp hybrid points is in the opposite direction. This direction and another one is right side directions, but in 180-degree angle in between these directions. And very small negative lobe. This is the negative lobe. So this is very small. Positive lobe, these two are positive lobes. This is greater size compared to the negative lobes. Now we'll give one example that Sp hybridization of BeCl2. The ground state configuration for beryllium is 1s2, 2s2, we know. And in excited state, one of these electrons in this 2s orbitals is promoted to vacant 2p orbitals to account for its bivalency. And one 2s and one 2p orbitals get hybridized to form the two sp hybridized orbitals. In beryllium, it has 2p orbitals also, which is vacant. So in excitation of these beryllium atoms, from the 2s orbitals, one electron is shifted to the 2p orbitals to form two numbers of sp hybridized orbitals. And these two sp hybrid orbitals are oriented in opposite direction. You can see this is the opposite direction. This is one sp hybridized orbitals. This is oriented in left side, and it is the positive lobe part will participate for the sigma bonding formation with the chlorine atom, and another sp hybrid orbitals in right side. For this also positive lobe of beryllium atoms will participate with the positive lobe of chlorine atoms, p orbitals, to form the another sigma bond. And this is called axially because through axis bond formation is happening in case of BeCl2. Now we'll discuss about the Sp2 hybridization. In Sp2 hybridization, one s orbitals and two numbers of p orbitals will participate to form three numbers of Sp2 hybridization. We'll consider that boron trichloride. In this molecule, for the boron central atom boron, its ground state configuration we know 1s2, 2s2, 2p1. So in the excited state, these 2s electrons promoted to the vacant 2p orbitals. As a result, boron has three unpaired electrons. And these three orbitals, that means 1s and 2p orbitals, these three numbers of orbitals hybridize to form the three numbers of Sp2 hybrid orbitals. You can see this right side, S, P, Py, Pz participate to form three numbers of Sp2 hybrid orbitals, and which is planar in nature. All orbitals direction is only in one plane. That's why it is the planar in nature. And bond angle, when it will form finally, it is a 120 degree. You can see that positive lobe, this area is much more than the negative lobe in case of Sp2 hybridization, and this positive lobe will form directly sigma bond to the positive lobe of the p orbitals of this chlorine atom, 3 numbers of chlorine atoms. So formation of the molecules is BCl3. As I already discussed, that 120-degree angle for the one sigma bond to other sigma bonds, and so the trigonal planar arrangement for the shape of this Sp2 hybridization. Here it is written Cl BCl, this bond angle is of 120 degree. Now we'll discuss about the Sp3 hybridization. So Sp3 means 1 s orbitals and 3 numbers of p orbitals will form 4 numbers of Sp3 hybrid orbitals. Example, previously already I discussed CH4 molecules. For the CH4 molecules, the central atom carbon, in this case the mixing of 1 s orbitals and 3 numbers of p orbitals of the valence shell to form 4 Sp3 hybrid orbitals of equivalent energies and shape. But remember, always you have to mention equivalent energy and shape when we'll talk about the hybrid orbitals. And right side you see that 1 s orbitals and 3 numbers of p orbitals px, py and pz. This is Sp3 hybridized to form hybridized orbitals of equivalent energies and shape. And then the bond angle, this angle is 109.5 degree from each other, and these positive lobes of this Sp3 hybrid orbitals will form methane with 4 numbers of hydrogen atoms, s orbitals, 1s orbitals. 3 hybridization, s character is 25% and p character is a 75%. Calculation, if you consider the hybridization is 100% and then 1 number of s orbitals and 3 number of p orbitals, so 1 plus 3, that means 4, so 100% divided by 4, and then it is a 25% which is for the s characters and 75% for the p characters. And the 4 Sp3 hybrid orbitals so formed are directed towards the 4 corners of the tetrahedron. And tetrahedron, we know its angle is 109.5 degree. Simple geometrical arrangement from this we know. I hope that you understand this hybridization in this class very clearly, especially for the s and p orbitals participate to form sp, sp2 and sp3 orbitals. Thank you so much for watching this class.